Hello, my name is Virgil Goldberg and this is my Physics 2212 Lab 2. So as a little introduction, it's very similar to Lab 1, and the purpose is to visualize the transfer of electric charges through the experiment that we've already talked about in Lab 1, so I won't go into detail about that. Then we will use a computational model to compare real life and a simulation. We'll also see the impact of real life environment and interactions on a certain system and experiment, and then we will compare the differences between a charge rod and a point charge particle model, as the difference is significant, because we will see as a little preview of the result that the difference between a charge rod and a point particle model is significant and cannot be omitted. So here are the few physics principles. First one is charges, so positive and negative charges. The other one is Newton's law of gravitation. So all we need for this experiment is that F is equal to the mass times the gravitational constant. We also need to know Coulomb's law, that the force is equal to kqq over r squared, or is equal to the receiving charge of the force times the electric field from the other charge. Now the electric field from a rod is equal to this bigger formula here, and with this is our hat. I forgot to add the hat on it. And if you want to find the force, you can just add the other charge here, or in our case, because they're the same charge, it would be q squared. So here's the experiment. So as a little overview, the system is tape B, and the environment is the Earth, which creates the gravity, and tape A, which is similarly charged to B, that repels the tape B to keep it in equilibrium. So the tapes are considered as charge rods and not point charges like last time. Air resistance and friction are not taken into account, and we assume that both tapes have the same charge. So here are the experimental steps used to create the tapes and do the experiment. I've already went into detail in Lab 1. In other words, we just create two charged tape. We check their charge with our hand, we stick it on a bridge and keep the one below it, record the distance apart and all other constants, and we can then proceed to calculations. So here were the data results. So we have the mass, the distance between the tapes when it reaches equilibrium, and the charge of electron, the area of the tape, etc. And here are the calculations. So first we found the force of gravity on the tape, and here we have the charge on one tape if it was considered a point charge, and here is the one with if it's considered a rod, and we see there's a significant difference that we'll talk more about later. Using the charge rod model, we see that there's about 1.45 times 10 to the power of 8 electrons delocalized. And with this amount of atoms, we can see that there's one delocalized atom for every 6 times 10 to the 6 atoms. So here's the coding simulation. We can see here the different constants. So gravity, K, the mass, and the charge, as well as the distance measured. Here we calculate the electric field created by the tape. Here is scalars, and I forgot to add the creation of the different arrows. And here we have the calculation of the dq, so every point charge along the rod. So we add up every, we'll say, field from every point along the rod, and they're, we'll say, represented by arrows here that show how the field interacts with it. So then we have also these two large arrows that we have coded here that tell us the force of here, the electric repulsion force, and here the force of gravity, and they need to be about the same size if we want to reach an equilibrium. You can see that the values here are fairly similar. So this one is the one that I previously calculated on the previous slide that we can find here again, and here. The other one is the one I hard-coded to figure out which value would come as close as possible. And so this is the value that the computational model will say gives us as the charge. So as a comparison, both results from the coding and the real-life experiments are very similar. And this is normal because they use the same original value input. And some sources of error are that the tapes are considered as rods and that in reality they're not rods, they're planes. We also assume that both tapes have the same charge, even though it's not necessarily the case, because while they're created with the same system, there's a lot of, we'll say, interactions with the environment that can change the charge. There might also be measurement issues, mismeasurements on my part, because I cannot measure to smaller than a millimeter. And we do not take into account friction, for example, with the pillars that hold the top tape. So here's an extension. What if you had modeled each of the tapes as a single point charge like in the previous lab? So if we compare them, we see that the point charge is 1.05 to the power of minus 8, and the rod is 2.32, which is more than double. So you can see that there's a significant difference between the two. And so why do they differ so much? It's just because we use different methods, and one is more accurate than the other. The other one, the point charge just gives you a very brief estimate, while the rod gives you a more, we'll say, close to life estimate, which makes it more reliable as it's the closest to what the tapes look like in real life. Thank you very much.